And an alternating series looks something like A1 minus A2 plus A3 minus A4, which we can write as minus 1 to the n plus 1 times an. Or it could alternate in the other way. Which just looks like minus 1 to the n times an. So if we have a series that bounces back and forth, back and forth, back and forth, we know a couple of things. This series converges if it is decreasing, meaning that AK has to be bigger than AK plus 1. As you move down the line, they get smaller. And its limit of the kth term is 0. Furthermore, if we have a convergent alternating series, so for any convergent alternating series, we have that the difference between the sum of the infinite series and the sum of the first n terms of the infinite series, the infinite sum and the partial sum are as close as the term that you leave off, or the next term in making that sum. So Sn is the sum from A1 through An, with the alternating part included. And this is the term that you truncated. Then we had that not all non-positive term series are alternating. We had some series where several terms are positive, then several are negative, then several are positive, or some wishy-washy mix-up of positive and negative terms. For those kind of series and alternating series, we compared the concepts of absolute convergence. The series is absolutely convergent. If it converges in absolute value. If a series is not absolutely convergent, it could possibly be conditionally convergent. For us, if we can't find the series absolutely convergent, we can check conditional convergence with this alternating series test over here. If a series is not absolutely convergent and not conditionally convergent, then it's just divergent. So we check this first, then we check that. If it's not that, otherwise, the series is divergent. We also had a couple other ways to check whether or not a series was absolutely convergent. This is the definition of it. But then we had a generalized ratio test and a generalized root test that put the ratio and the roots in absolute value. If any of those series show that this, give you a convergent series, then we say that that series is absolutely convergent. So a generalized ratio test looks at the limit as k goes to infinity in absolute value of the ak plus 1 divided by ak. That limit's going to be some number L. If L is smaller than 1, the series is absolutely convergent. If L is bigger than 1, the series is not absolutely convergent. And you go to check conditional convergence. So check for conditional convergence. And as usual, if L is equal to 1, then go back and try something else, preferably this. We had a similar statement of the generalized root test. So the same 3 conditions for the generalized root test. But in the general root test, we find the number L by taking the kth root of the absolute value of the AK terms. And then the same 3 checkpoints. So that's where we were. All right, we're back. All I wanted to do was open up my notebook, get some notes out of it. Let me shut the camera off. That's the last thing. Okay. So what I want you to do in each of these I want you to tell me in each of the following decide if the series is absolutely convergent. I'm going to denote that AC. Conditionally convergent or divergent. Absolutely convergent will be our AC. Oops, that's absolutely convergent. This one's conditionally convergent or divergent. So for the first one, let's just say number one. Oh, I gotta move my rag. So as you're writing this down, can you tell me what type of series is a good candidate for the ratio test? Did you know when to use the ratio test? Or just anything? The hint is we need things to cancel in a ratio test. Multiplication, powers of n, or factorial. We don't have any of that here. So the way I'm going to test this for absolute convergence is just taking the absolute value of it, which gets rid of the alternating part. So first, check for absolute convergence using the absolute value. And so if I take the absolute value that this is positive, that's going to go away. So we're just looking at the natural log of k divided by k. Does anybody know if that series as a positive term series is convergent or not? Q log, anybody thinking Q log?
One make it divergent.
One makes it divergent, just like a P series. This is a divergent Q log series. Okay, but this is a divergent Q log series. The Q that we're talking about is a power on K. Q is 1. It needed to be strictly bigger than 1 for this thing to converge. So our conclusion here is that it's not absolutely convergent. So now my second step is to see if it's conditionally convergent. And it's an alternating series, so we're going to use the alternating series test. Use the alternating series test right up here. So there's two things to check. We need to check if it's decreasing. Well, it's hard to see if it's decreasing to me if I just increase each k by k plus 1. I'm going to show it's decreasing by showing that the derivative is negative. I think we did this in class last time. Oops. I'll use x's. I'm going to show that that derivative is negative using the quotient rule. The natural log of x over x. So we have the bottom times the derivative of the top minus the top times the derivative of the bottom. Derivative of x is just 1 over the bottom squared. And so our derivative looks like 1 minus the natural log of x over x squared. And as long as x is bigger than the number e, the numerator is going to be negative. If x is bigger than e, say I plug in e squared, natural log of e squared is 2, 1 minus 2 is negative, x squared is positive, so it is decreasing in the long run. So it is decreasing. Now we see that the limit goes to 0 because, how can I make the big jump and say that that limit is 0? K grows faster than log of k. If you don't believe that, do L'Hopital's rule. The derivative at the top is 1 over k. The derivative at the bottom is 1. 1 over infinity will go to 0. So it is conditionally convergent. This series is conditionally convergent. Okay? I'm going to run way back over here, and we're going to try another one. Move that over there. Move that over there. Do that. Leave it over here. Okay, let's scroll back. Scroll back. All right, let's try the second one here. -3 to the k times k plus 1 divided by k factorial stay right here. This is the part that makes it alternating. You can think of -3 to the k as -1 times -3 to the k, which is -1 to the k times 3 to the k. But this one has k powers, multiplication, and factorials. So this time I'm going to check for absolute convergence using the ratio test. So we'll check for absolute convergence using the general ratio test. So let's set up the limit as k goes to infinity of ak plus 1 divided by ak in absolute value. So to do this limit, we replace each k with k plus 1. I went too far over there. That ain't gonna work. I gotta move it over. Bugger. Let's move it over. Go. Okay, so I'm going to go up here and replace. You guys can't even see the problem. Let me write the problem down over here. Oh, fudge. There's our problem. So we're going to go in there and replace each k with k plus 1. Stick it in absolute value bars. So we're going to have negative 3 to the k plus 1 times k plus 1 plus 1, which I'll write as k plus 2, divided by k plus 1 factorial. That's going to be the top thing here. Then we have to divide by our series. So let's make the jump to the step where dividing by this is equivalent to multiplying by the reciprocal. So I'm going to put the k factorial up here, the negative 3 to the k, and the k plus 1 here. So let's see if you remember this, that I can write negative 3 to the k plus 1 as negative 3 to the k times negative 3 to the 1. I can write k plus 1 factorial as k plus 1 times k factorial. Remember doing stuff like that last week? And now I can put this back in here and you can get a better look at how things will cancel. Thank you. It's that guy. So the k factorials and the negative 3 to the k both cancel. So that one cancels that one. K factorial cancels. This negative 3 can become a positive 3. So I have 3 times k plus 2 over k plus 1 all squared. Can you tell what that limit is without me having multiplied out?
0.
Good. It's bottom heavy, so that limit is 0. If the general ratio test gives us a limit that's smaller than 1, what's our conclusion?
Absolutely.
This series is absolutely convergent. Let's go with number 3. Number 3, we'll look at the series. Negative 1 to the k. Let's go here with a 2 to the 2k, all divided by 2k factorial. So I see the factorials, and that's going to make me say I'm going to do the same thing. I'm going to start with the generalized ratio test. So see if you can set up the general ratio test doing this for this problem. Replace each k by k plus 1. factorials and or n powers are a good clue, or k powers. Try setting it up yourself, don't look at me. Looking at the limit as k goes to infinity of the absolute value, k plus first term of n kth term. Since it's an absolute value bars, we know that this thing's going to disappear, right? So let's not even include that in it. It's going to be gone. That's just a negative one every now and then. So when we stick that in absolute value bars, that's going to cancel. It's going to be gone. Let's just worry about what those look like. So we're going to have 2 to the 2k, but we're going to replace the k with a k plus 1. And then we're going to have a 2 times k plus 1, and then all of that factorial. And then we're going to multiply it by 2 to the k factorial over 2 to the 2k. So I can write that first term up there as 2 to the 2k times 2 to the 1. This is going to be 2k plus 2 factorial. How do I cancel there with the 2k factorial and then 2k plus 2 factorial? What's left?
A 2k plus 2 and a 2k plus 1.
Good, good. That cancels here, leaving me 2k plus 2 times 2k plus 1. That cancels there. So I've got 4 divided by that stuff there. K's are on the bottom, so that limit's 0. So just like before, if our limit is smaller than 1, we're done. Our series is absolutely convergent. Everything that is absolutely convergent is also conditionally convergent. All right, let's try this next one. What number am I on? 4? k factorial over negative 5 to the k. K power, k factorial, let's go ratio test again. Let's tell us that we're going to check for absolute convergence. Make the general ratio test. So we're looking for the limit as k goes to infinity of the absolute value of the ak plus 1 term over the ak term. That'll be the limit as k goes to infinity of k plus 1 factorial divided by negative 5 to the k plus 1 times negative 5 to the k over k factorial. Reduce that for me and tell me what you end up as your reduced expression.
K plus 1 over 5.
K plus 1 over 5, very good. K plus 1 factorial cancels with the k factorial, leaving me a k plus 1 on top. This one here cancels with that one, leaving me negative 5 to the 1, but it's an absolute value bars. And then I canceled that one. So what's that limit? Infinity. So this is not absolutely convergent, because that's bigger than 1, right? So now let's do the alternating series test to help us check for conditional convergence. Alternating series test. Is it decreasing? Does it have a limit that goes to 0? So let's just go and rewrite our series like this. You agree that those two say the same thing? Is that negative 5 to the k the same as negative 1 times 5 all to the k, which is negative 1 to the k times 5 to the k. Dividing by negative 1 to the k is the same as multiplying by negative 1 to the k, because all that does is flip the sign back and forth. So in the alternating series test, we look at that second bit here, the non-alternating part, and we check if it's decreasing and has a limit to 0. So instead of checking for decreasing, I'm going to do this one first. So I know that limit's not 0. Why not? K factorial grows faster than things to the k power.
Check that like first.
Yep, could have checked that first, yes. Did you see that when I was writing it down? Maybe? So it's not absolutely convergent. Not conditionally convergent, sorry. So this is a divergent series. series diverges. And so let's look at one more. Same instructions. So this doesn't have factorials or k powers, so I'm going to shy away from the ratio test. I'm going to go ahead and check this for absolute convergence by just taking the absolute value of it. So we're looking here. Now we're back into our list of positive term series. Actually, that should be an absolute value because the tangent does change sign. Do you think of a test you might want to use? I'll name all of your tests. It's not a P series, a P log series, or a geometric series, so the easy ones are gone. It doesn't look like anything I want to integrate. Be quiet, Siri. So I lost track. I don't want to integrate it. I don't even think I want to compare it with a direct comparison or a limit comparison. What test do you think I'm leaving out so far? Ratio, root, those don't apply. Skip it. What about your favorite test? I always said you need to check things using the test for divergence first. I'm a little bit suspicious that this doesn't have a limit that goes to 0. But let's see. Maybe it does. Let's just see. Let's try the test for divergence. Let's see what the limit is. As k goes to infinity. I think it's going to have a limit that goes to 0, but let's continue. 1 over k is going to go to 0. What's the tangent to 0? Tangent to 0 is 0, so this looks like infinity times 0. That's an indeterminate form. We fix that by taking this k and putting it underneath as a 1 over k. And that looks like 0 over 0, and we can do L'Hopital's rule. You take the derivative of the top and divide it by the derivative of the bottom. It's been a while. Do you know how to take the derivative of the tangent of something? Secant squared of that stuff. So I get the secant squared of 1 over k. Then I have to take the derivative of the 1 over k, and I get a negative 1 over k squared. Derivative of the bottom is also a negative 1 over k squared. Secant is squared. These are going to cancel. So I don't need the absolute value bars. One over k goes to 0 as k goes to infinity. What is the secant of 0? It's 1. So secant squared of 0 is also 1. Then it's not equal to 0, so this series is not absolutely convergent. It's also not conditionally convergent because if I do the alternating series test, one of the things that we need is for the kth term to have a limit to 0. So it's not conditionally convergent either. For the same reason, the kth term does not have a limit of 0. And so this is a divergent series. Any questions? Anybody? All right, then the bit that I wrote there at the bottom when I first started, that if you have a convergent alternating series, you can approximate the sum of the series by using a partial sum. If I use 8 terms of my partial sum and add them together as an alternating series, it's within the actual sum by whatever size the 9th term is. So I'm going to take a series that's an alternating series, but it's also a geometric series. And we can compute the exact sum of a geometric series. We can use the idea of approximating the exact sum with the n terms. So I can show you how closely we get to the sum. So for the series, sum from k is equal to 1 to infinity of negative 1/3 to the k plus 1. Estimate the sum of the series by taking the sum of the first 4 terms. And then I want to know how accurate is this estimate. And we can tell how accurate it is because we can compute the actual sum and we can use the theorem that I wrote down there earlier. We And use the fact that for a convergent alternating series, the actual sum differs by the sum of the first n terms by no more than the n plus first term. Would you have been able to recognize this as a geometric series if I hadn't told you? Hopefully, we have a constant, a -1/3 to a k power. That's the giveaway that it's geometric. If you're not sure that you see that, we just start putting numbers in for k. If k is 1, this is a square, so I get -1/3 squared. If k is 2, I have -1/3 cubed. K is 3, I get -1/3 to the 4th. So it's a geometric series where the first term is -1/3 squared, and my common multiplier r is -1/3. It's an alternating series because of the -1. It's a geometric series with a is equal to -1/3 squared, r is equal to -1/3. The absolute value of r is smaller than 1, so it converges. So it is a convergent alternating series. So I'm going to find the sum of the first 4 terms. I've got the first 3 terms there. The sum of the first 4 terms is called S4. So I need to add one more on here. It's going to be -1/3 squared plus -1/3 cubed plus -1/3 to the 4th. Next one would be -1/3 to the 5th. So I have a positive 1/9 minus 1/27 plus 1/81 minus 3 times 81 is 243. So I guess I'm going to get a common denominator of 243. Unless somebody wants to do this on a calculator for me. Then I don't have to do it. Anybody have a calculator handy? Then I don't need to get a common denominator. You just take 1/9 minus 127 plus 1/81 minus 1/243. Give me as many decimal places as your calculator tells you. Say it again, please.
Is it 22/243?
And what's that as a decimal? You just did that by brute force?
I think so, because like each one would have like 3 times more in the numerator if you made it.
Right.
So it's like not 1/9 would be 27/243. And then
Right.
minus 9/243 plus 3/243.
Good. And so what is this as a decimal? Do we have it? Yes, sir.
My calculator gave me 20/243.
20?
Yeah, just.
That's pretty admirable, though. That's pretty dang good. And what is 20/243 as a decimal?
0.0823045267.
I'll stop there.
That's as far as we go.
That's as far as we got. As far as I got it in my head, too. I just got all that. Okay. Now, according to this, that amount, that sum should be smaller than the next term. What would the next term be? Well, shoot, that's easy. -1/3 to the 6th, right? Negative 1/3 to the 6th would be smaller in difference. Oops, I didn't mean to say it that way. I need to say it this way. The actual sum minus S4 is smaller than A5, that's A1, A2, A3, A4, so A5. So S minus S4 is smaller than negative 1/3 to the 6th, which is, let's see, positive 1/9, 12, 6, 729. Now I need that as a decimal. 1/729. Please, calculator. You done put your calculator away? 1/729.
0.00137,174.
All right, so this decimal place is accurate. This one's accurate. I won't round up till I get to here. So I've got 4 decimal places of accuracy. And since this is a geometric series, we can actually find S. This S. We can find this number and see how true that is. So here S is A over 1 minus R. A is 1/9. R was a negative 1/3. And so I've got 1/9 divided by 4/3. So that's 1/9 times 3/4. So that's 1/12. So now let's see how close this number is to 1/12. So they give me 1/12 as a decimal. 0.083 repeating. So I said we're good to here, but then I lied because that would round that one up. Pretty dang close, huh? So we're good to about right here. Okay. Questions? That's only true for alternating series. Can't use this idea for non-alternating series. And this is only true for geometric series. Okay, that takes us through section, where am I, 8.6. Through section 8.6. Let me kind of give you a heads up of what's coming up next. Section 8.7, power series. Let me see. I don't want to get you guys too far ahead of my other fellers. Let's see where we are. Today is April, what is today? 5th, 9th, 7th. 7th, and I said work number 4. Which one's number 4? This one. I did that. going to take the concept of our infinite series and we're going to introduce an additional term to make this a function of x. So a power series is an infinite polynomial. Right, a polynomial looks something like this. It's going to have a lead coefficient, a constant term, plus a constant times x to the first power, plus another constant times x squared, plus another constant times x cubed, and so on. That's a power series centered at x is 0. Now I can shift things to the left or the right by adding or subtracting a number from x. If I subtract a number, it moves it to the right. If I add a number to the x, it moves it to the left. So this is a power series centered at x is equal to c. C is a constant. This one we said was centered at x is equal to 0. And this one was centered at x is equal to c. Depending on these terms, these polynomials have an interval of convergence. There'll be an interval centered around that x for which this polynomial converges as a power series, as an infinite series. Outside that interval, the series will diverge. So let's talk about the one centered at the origin. The power series centered at the origin does one of three things. It is possible that it converges for all x. Or it's possible that it converges only for x is equal to 0. But how boring would that be if all the x's were 0? Then all you get is this first term. Or here's the biggie. It converges absolutely for some x in an interval I don't want to say some, for all x in the interval. Say from minus r to r. I wrote it as an open interval. It could be a closed interval. It could be a half open interval. So this interval could look like this, or this, or this. That's going to be some picky detail we'll have to measure. It converges inside that interval, open or closed, or half open or half closed, and diverges everywhere else. The number capital R that I'm using is called the radius of convergence. And for this particular power series, it describes an interval around 0. So it's going to converge in here and possibly at the endpoints, but diverge out here. The same thing can be said about this one, except for we just shifted over C units. So this would be the number C plus R, and this would be the C minus R if we were outside the origin.
The radius?
Radius. It's a radius because if you think of this as part of a circle, and the radius goes from the center out. So that distance is R in each direction. And you'll find that for a power series, on its interval of convergence, you can do all the good things that you can do with polynomials. You can add them term by term. You can do term by term substitution. You can take the derivative term by term. You can take the antiderivative term by term on its interval of convergence and get something that still maintains the same level of convergence. So what we're going to get used to doing here at the beginning is discovering what the interval of convergence is. Is it just the whole number line, a single point, or some subset? Then once we get the hang of that, then we're going to build these power series ourselves. We're going to see in section 8.8 that if you have a continuous function whose derivatives are continuous, then we can write such function as a power series. And it converges to that function exactly on its interval of convergence, which means it has the exact same behavior as that function on that interval. Doesn't that sound like fun?
Yeah. So much fun.
I could take you anywhere. You guys are a lot of fun. These things look like stuff with powers. So we're going to try to find the interval of convergence using our ratio tests with the absolute value. We'll find this interval of convergence using the ratio test. Here's an example. Consider power series from k is equal to 1 to infinity. Doesn't matter whether I start at 0 or 1. This one I'm going to start at 1 because I'm going to have a k cubed in the denominator. K squared. X to the k divided by k squared. I should go x to the k minus 1 so I get a constant first. So let's write out a few terms so that you know what this polynomial looks like. X to the k minus 1 divided by k squared. So if k is 1, I get x to the 0. X to the 0 is 1. 1 over 1 squared. So my first term is just 1. Now if k is 2, I get an x over 2 squared. If k is 3, I get an x squared over 3 squared. Then if k is 4, I get an x cubed over 4 squared, and so on. Let's see if we can find the interval of convergence. Which I said we use the general ratio test. We want to see where it converges. So we want to see where the ratio of the k plus first term over the kth term is smaller than 1. We want to only consider the case where it's convergent. So we're going to solve for x in the expression, the limit as k goes to infinity of ak plus 1 over ak, and we want it to converge, so we make L 1, and we want to know where this expression has a value smaller than 1. So it'll look like this. I'm going to go up here and replace each k with k plus 1. So I'm going to have x to the k plus 1 minus 1 divided by k plus 1 all squared. X to the k plus 1 minus 1 is just x to the k divided by k plus 1 squared. Then we divide that by the kth term. So that would put us a k squared up here, and then an x to the k minus 1 here. We want to know what values of x make that limit smaller than 1. So we can think of x to the k minus 1 as x to the k times x to the minus 1, and the x to the k's cancel, leaving me an x to the minus 1 down there. And so I have a limit as k goes to infinity of k squared over k plus 1 squared. This x to the minus 1 is on the bottom. I can move it to the top and make the exponent positive. And I'll give it its own absolute value bars. Because it doesn't have anything to do with k. In fact, I could have taken this term and put it out in front of the limit. It has nothing to do with k. Here's the only part that has anything to do with k. So you're looking at this part, and you can tell me what that limit is. That limit is 1. They're both an x squared term. So that limit is 1. So now we're solving the inequality. 1 times the absolute value of x is smaller than 1. This number 1 here is called the radius of convergence. The absolute value of x is smaller than 1 means that x lives between 1 and -1 on the number line. Now I need to check the behavior of my power series at each endpoint to see if I need to close up one or both of the endpoints. So that's my next step. We need to check the endpoints of this interval for convergence. If x is 1 and if x is -1, does that original series converge or diverge? Let's see if I can do that real fast. So if x is 1, I have 1 to the k minus 1 over k squared. One to any power is 1, and so we get 1 over k squared. What's your conclusion on this series? Does it converge or diverge? It's a convergent p series. So that means I color that one in. Now if x is -1, my series looks like -1 to the k minus 1 over k squared. What do you know about that one? It also converges. This is the alternating p series, and we said all alternating p series converge no matter what the power is. Alternating p series. So this is a particular power series whose interval of convergence is the closed interval surrounding 1 and -1. Okay? Okay, so my plan for our next class is to take a step back. I'm going to give you a worksheet with a whole bunch of series on them. And I want you to see if you can describe cleanly whether the series converges or diverges and what test you're using. We're going to practice in class. So I'll have a handout ready. Maybe it'll be a blackboard. I might ask you to run it off, but at least run off the power series tests with positive terms so that you have that little handout looking at you. We're going to kind of backtrack and review.
So,
Oh, give me some?
oh,
It's
yes,
real.
and also the question.
Okay.
All right, so on the 840 works, number 1 and number 2, they want you to like plug in your AK and your BK for the limit comparison test.
Right.
And I'll plug it in and tell me it's wrong, but then I do it anyways. And the last
Sometimes
two
they-
problems will be right. And I'd be like, what the heck?
Sometimes they want you to throw the constants away. Like I'm using things like 5 over k squared as my BK.
Are you talking about?
Just
the
use
one-
the 1 over k
Yeah,
squared.
it's just one of, I was so confused if I was working.
Yeah, they want you to use it.
X to something.
They want you to use use it without the constant.
Even where it says AK, when you put in AK, that's like the original series, right?
Right? You could put the constant in there.
It would tell me it's wrong. I'd be like, what the heck?
I'll need to take a look at it.
Here's me doing it, and it works.
Yeah, let me see. Let me see. Let me stop this first.
It's not that homework, so, and it's a little bit late to ask you this question because I already signed up, but, do you recommend, for my hours, I'm gonna be taking calculus over the summer. Is that a good idea?
Cal 3?
Yeah.
Yeah, I mean, you're gonna be busy because it meets every day for 2 hours. Every
It's not
day.
exactly that bad. I think
Okay.
it's like an online thing.
An online thing, gag.
maybe.
Yeah, the online classes are all summer.
I'm confused about that because it doesn't have meet time. Do you do meet time?
If there's no meeting time, then it's not
You
not
just
going to
do
be
it.
synchronous. It'll be asynchronous
I
when
took
you.
a history class last summer and you just, I don't even think they email you stuff. You just do it. They'll post everything and then you can get it done at your own pace.
Yeah, so like so you would pick your BN just to be N cubed over into the 4. You leave the 7 and 3 off, and you leave, this is your AN. But you leave the 7 and 3 off, and that should work.
I feel like I tried all possible combinations. Maybe if I do this, maybe if I leave these out, maybe it's
Okay,
this.
I'll take a look at it and see what you've written.
I've got like 20 attempts.
There was
I'll
one
go try.
problem on like this where like I think it was actually problem 8, right? I did it and I got the right answer several times, but I put it in probably close to like 15 times. And it didn't like it. I tried to make it, I didn't like it till the last time, even though I had the right answer. I think that's just wonderful.
I think for this one, instead of saying it's divergent, Weber wants you to say that sum is infinite.
Well, they said, there was like multiple girls say like, oh, put like I and F. And so I put I and F and it just didn't like it.
Oh,
And I was like, I did the math 5 times.
I'll go,
But
yeah.
eventually, like, I figured it out.
But
I
you were able to
put it
get
in,
it?
and I was like, okay. But I
Okay,
don't know why.
well, Merrick, I'll look at what's going on.
Thank you.
Here's
Maximum
your other
likelihood.
one.
Oh, nice.
And where did I put the rest of them? I walk with papers. There's your other one.